So I'll use one of these examples or one of these questions from your homework to demonstrate that shortcut. So if you like, I don't know, let's pick one. Let's pick a bigger one. Sulfur looks like a biggish one. If you look at sulfur, sulfur is in row 3. So once we get the nucleus, it's going to be P equals 16. N is also going to be 16. Because we're drawing an atom here, what the shortcut will let us do is the shortcut will let us say, okay, well, we're in row 3, so we need to have 1, 2, 3 shells, and we can put those down immediately. Because of the row that sulfur is in, that's what we can do. And then when we take a look at the group number here is 16. So if you look at the ones number there, that's a 6. So what that means is sulfur is going to have 1, 2, 3, 4, 5, 6 on the outside, and then everything under that's going to be full. So the inner one's going to have 2, this one's going to have 8. And it's a quick way to draw your Bohr diagrams if you're comfortable with the periodic table. That's the shortcut. Questions about the shortcut? If you don't like it, if it makes your life more difficult, don't use it. But it is another way to think about where these Bohr diagrams come from. And then for the ions, the shortcut's a little bit different. The thing about the ion is, regardless of the ion, that outside shell also needs to be full, always needs to be full. So when you drew these things, one of the things you could have noticed was every outside shell is always full. When the ions are positive, it loses that outside shell, goes down a level. When it's a negative ion, that outer shell gets full. So again, we've got a shortcut there too. And I can show you what the shortcut would look like on something like, I don't know, let's do magnesium. Magnesium is P equals 12, N equals 12. And then rather than doing magnesium the way we were doing it when I was here on whatever 2 days ago was, Tuesday, the shortcut would look like this. Well, I would say, okay, magnesium is in row 3, but the ion is positive. So rather than having 3 shells, it's going to lose that outside shell. It's just going to have 2. And those shells have to be full. Boom, 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 boom. It's a lot less to think about, and then we can throw the charge outside. Okay, well, it's going to be plus 2. Because that's the ion charge listed on the table. It's the shortcut. It's just another way to think about how these things get drawn. I guess it's not so much a shortcut. It's just a different way to do it. Questions about the shortcut? Yes. Just stretching the shoulder. Okay, cool. And then yesterday, Mr. Brad and I, you were supposed to write my things down. We didn't do it. Yesterday, we reviewed ionic and covalent compounds. Something else that should have been reviewed from grade 9. Ionic compounds are always a metal and a non-metal. So the metal likes to give up electrons. The non-metal likes to take electrons. It works out well. So the metals give. They lose that outer shell to fill up the non-metal shell. Questions, comments, concerns about any of this stuff? Okay. Please stop me if you do. The covalents are always non-metal and non-metal. They both want. And they both want, but they're willing to share. So if they're willing to share, then as long as they're close enough to each other so that they can both claim each other's outer electrons, then they will both be happy. Metals and metals will never do this because metals want to give up and they don't want to share. They just want gone. So metals behave differently. They don't bond like this. So then these things, so all you have to start, I had you guys identify what kinds of ions these things were. All you have to do is say, okay, well, do I have 2 nonmetals? Do I have a metal and a nonmetal? And then identify whether it was ionic or covalent. Questions about any of this? Okay. And then I wanted you to start drawing some Bohr diagrams of these things. So the Bohr diagram here for lithium, the example he would have gone through, this is lithium, this is fluorine. And so the steps I want you to go through is to draw each one, draw an arrow from the electron that's leaving the metal to where it would join the nonmetal, and then redraw the two ions. And then the reason they stay together is because opposite charges attract. You have a positive charge here and a negative charge here. You would look at that in physics. Questions, comments, concerns about that? Okay, I'll flip the page. So then the last example he would have done with you guys, or should have talked to you guys through yesterday, was something like this. We've got a Bohr model of O2. O2 is just two oxygens. So oxygen's a nonmetal if you got two of them. It is we call these things diatomic because it's two of the same atom, but it's a covalent because it's two nonmetals. So you draw these ones a little bit different. You draw the individual oxygens, and then instead of drawing the transfer, because they don't transfer, you draw I wanted you to circle a pair that would share. They always share in pairs. So these two could share, these two could share, and then we draw them with the overlap. Covalent compounds are terrible to draw using Bohr diagrams. That's just as a rule of thumb, they just are. And so there's another tool that I'm going to show you today that actually makes these drawings so much easier. Okay, so there's questions about the 5 he assigned for practice. Someone had asked a question about hydrogen. Which one are you? Who had a question about hydrogen? Brooklyn? No, Evelyn? Someone from that back table had a question about hydrogen. Okay. So then you were asking about this guy here. Is that thing ionic or covalent? That is a phenomenal question. Hydrogen's an iffy one because if you look at the periodic table, it actually shows up in both spots. Unfortunately, it's not that easy. So for hydrogen, I will tell you what the compound is. Because my chemistry knowledge is not insignificant, but it is not enough to answer that question fully. It has to do with a concept called electronegativity. So there are, which we don't cover in Science 10. You'll look at it when you hit chemistry grade 11, chemistry grade 12. But the short answer to your question, Evelyn, is depending on how badly the other atom wants the thing, that determines whether or not it gets ripped off or not. So in this guy, in H2O, the electronegativity of oxygen isn't enough to take from the hydrogen and make it a metal ion. So this one, you would draw, it would look like this guy here. And I would tell you, this thing has to be covalent. And it would look like this. You draw a single hydrogen, there's your oxygen. It would loop. And then you would redraw it with the hydrogens moved to where this thing would be shared. And you get something that looks like this. An example of where that wouldn't happen would be something like this. So I'll put it actually in here. If you have room, you can do it yourself. If you had something like HCl. So oxygen is in column 16, I believe. Yeah, it's in column 16. I don't remember the value for the electronegativity. Doesn't matter. But this particular compound, HCl, is another compound. Hydrogen, the question is again, is it going to be positive, is it going to be negative? Chlorine has an electronegativity that's greater than oxygen. Chlorine is a vicious chemical compound. Well, element, vicious element. It wants to take stronger than oxygen is willing to take. And so it will actually rip the electron off of the hydrogen. This thing becomes ionic. And so you'd get something that looks like this. You'd have your hydrogen. You'd have P equals 1, N equals 0, and that's it. It would take away that outer shell, forming a positive 1 charge. And you'd get a chlorine that looks like this. P equals, I don't even remember what these numbers are, 17 and 18? Yeah. P equals 17, N equals 18. And then chlorine is in row 3, I believe. Yeah. 1, 2, 3. And because it's an ion, all those shells would be full. So you'd go boom, 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 and then you go boom, 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 boom. That's the long way. I guess I gave you kind of a longer answer. Yes, it is. Thank you, Brooklyn. So the shorter answer is, at this stage in your chemistry education, I will tell you whether hydrogen's behaving covalently or ionically. I will have to. Evelyn, does that satisfy? Is that a satisfactory answer? It depends on a concept called electronegativity of the second element, which is a concept we don't talk about in Science 10. An easy way to do it is to say if you're outside, I'll do it this way. If hydrogen is bonding to any of these things, it's going to be ionic. If it's bonding to anything left of it, it'll be covalent. Is the easy way to talk about hydrogen. Okay. How do we feel about, oh wait, I guess I should show you the rest of the answers. So the answers for the first two would look like this. Here's the first practice that you would have drawn. You would have had to identify that this thing was ionic. You draw your magnesium, you draw your oxygen, you draw where they move to, and then you redraw the ion of each. So there's my ion of magnesium, there's my ion of oxygen. For Cl2, you're doing 2 chlorines. Chlorine's a terrible one to draw because it's just so big. But you draw the 2 chlorines, so we'd say, okay, well, they each have space for 1. So those 2 loners are going to share. So then you would circle those 2, and then you'd redraw it so that they're butt up against each other, sharing that pair. Oh, someone snuck in. Who snuck in? Jedediah, was that you? Yes, it was. And Sahej, you also made it here. Okay. Questions, comments, concerns about either of these two? Okay. Then this page would look like this. This is something I didn't give you. I'm going to give it to you in a second. I did totally give it to you. This is a question. BEF2. So you'd have to identify that beryllium's a metal, fluorine's a non-metal. That little subscript there you would have looked at in grade 9. And you said, okay, well, that little subscript means I have 2 of the fluorines. So you draw 1 beryllium, 2 fluorines, and then you'd see, well, 1 electron from the beryllium is going to go to one of these fluorines, and the other one's going to go to the other. And then this is where, I don't know if Mr. Rad and I talked about this, and it's fine if you didn't. The way you want to draw these things, because it's an ionic compound, and this is a nitpicky thing that, had I been here yesterday, I would have mentioned. I wasn't, so I'm mentioning it now. When you draw an ionic compound with multiple atoms, with more than 2 atoms, ions, more than 2 ions, you want to draw them so it always goes negative, positive, negative, positive. The negatives aren't going to end up beside each other ever, because if you remember to physics in your Science 9, like charges are going to repel each other. the fluorine is going to end up on opposite sides of the beryllium. And you're going to get this, it's actually kind of a cool structure. It'll look like a crystal. So this is the one that Evelyn asked about. There it is. And then here was your answer number 5, the Li2O, where you have 2 lithiums and a single oxygen. The lithiums are metals, the oxygen's a nonmetal. And the 2 lithiums are going to give, you draw them in order, positive, negative, positive. Questions, comments, concerns about any of this stuff? How many of you feel like you could benefit from a little bit extra practice? Okay. No, I don't think you're the only one. And this is something I was going to do anyway with you guys today, because today's lesson is pretty short. Ooh, do I want it to be pretty short? Yeah, it can be pretty short. Okay, so here's what I want you to do. Sahib and I are going to float around. I want you, how many are I? 1, 2, 3, 4, 5, 6, 7, 8. I've got 15 board spots. I want you to pair up, or you can free up. In 2s or 3s, I want you to find some board space under one of the numbers that's up there. You can erase whatever on the board. And between the two, you're using one pen. So some of the boards have pens already, some of them don't. Grab a pen and a partner, or 2 partners, and move to one of the board spaces. Yes. You'll want your periodic table, or you can use those periodic tables that are up on the walls. You can reference those. I'm going to erase whatever's there. So there are, one thing. So some whiteboard etiquette for you guys. Because not all of you are familiar with the workings of the whiteboards. I will ask you not to use your hands to erase the whiteboard. Not because I care about your cleanliness. I do, but that's not why. If you use your hand to erase the whiteboard, you actually transfer oils from your hand to the board, which makes it harder to clean subsequently. It means I have to go around and spray every whiteboard. So for your cleanliness and for my don't wanting to do more work than I have to do, please use the erasers, or if you need paper towel works great too. Or if you're hell-bent on using something attached to you, your sleeve, don't use your hand, please. Okay. So I'm going to give you a compound, and I want you to go through the steps to draw each one. Draw them separately. And I don't want the same person using the pen the whole time. So if there's 2, one of you draws one of you draws the other. If there's more than 2, then we'll split it up. But I want everyone drawing. So your first one that I want you to draw is going to be Na2S. So write down the name Na subscript 2 and the letter S. Na2S. I want you to draw the board diagrams for Na2S. And that 2 should be a subscript down below, not a superscript like an exponent. Na, like this one. Na. Na with a subscript with a little 2 here. 2 down below. So if you put it down below here like this. I want you to draw. So him and I will walk around. He with some boards too, so we're using what? Okay. So I draw the board diagrams, identify what kind of compound you have, and then draw the compound. You need an eraser?
Oh, there it is.
Yeah, I will be giving you guys one. You can also use the ones that are on the walls. I want to hold on to those for a little bit. Yeah, hey, Messi. Messi's here. Messi is late. Okay. So draw the Bohr diagram for each atom, and then I want you to show the transfer of electrons or the sharing of electrons, depending on what you have. Is it ionic or is it covalent? Is it metals or is it metal and non-metal? Or is it non-metals or metal and non-metal? In the middle. It's what? So you still need the sulfur. There's no sulfur. Oh, there's sulfur. This is your sulfur. This is your sodium. How many sodiums should you have? And then I want you to draw the transfer. I want you to do all the steps. You're still drawing the seconds. Okay, how are we doing, gentlemen? Okay. This is a barrier. This is black. It's on this side. It's a non-metal. Everything on that side is. Or you can look at the charges. Metals are positive. Non-metals are negative. It's more like the erasers. Okay, so you've got your NAs, your NAs, those are good. When you're drawing, this is your sulfur. has 8. And how many are in the outside one? There should be 16 total. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12. Should be a 15 and a 16, right? And then so that's the always going to show line. So when you're drawing this thing, before you start substituting things or transferring things, is this Na2S going to be ionic? Okay, that's right. So that's what you have. That means this is going to be ionic. What is going on here? As it's ionic, these ones they don't circle and share. They give it. So it's here. So now you draw again. Like this, where you have an ion, where you have one. One is plus one. It's given the outside shell. If you look at these guys, they drew each and then once this thing leaves, once this one leaves, this outside shell is gone. Look at the tiniest. One right there. What? Yes. You have a question? Good. Exactly. These are two sodiums, ionic, ABM, and it's perfect. Okay. My only criticism on the this is correct. These individual ones are correct. But you only draw the circles around the share. These ones aren't shared. Those are actually double. This guy leaves. So what that means is that the metals to become positive one have to lose the outside electron. Outside shell should be gone. Probably should be gone on this side. And this should more stable. I did a very cool. So I have a better idea of this. Okay. Yes, love it. So we're almost on the three stones on this day. Okay. These look good. Keep going. Yes. Yeah, you have this guy going through here, and this guy going through. Yeah, perfect. And then you redraw them with the brackets around it. Okay, lots of you guys are ready to move on, so let me give you another one. I haven't had a chance to talk to every group. NH3. Ammonia. Draw me ammonia. NH3. Remember what I said to all of you about addressing Evelyn's question. If it's outside, if it's not in row 17, treat hydrogen as if it were a non-metal. It's outside 17, treat it like a non-metal.
Chair. You are very good. I'm very happy.
Okay. So again, the first thing you always want to decide is if this thing's ionic or covalent. You like pick it. Take it. You want it or I'm going to hand them out later, but you want it now. One end.
Three.
Is that it? Oh, no. Yes. N. H. My apologies. Beautiful, love it. Which one's this? So, the drawing nitrogen. He's going to this side. And then N is going to pull that number there, subtract that number. So 14 minus 7. 27. So this is my neutrons. This is protons. And then you draw one ring, 1, 2, 4, 5, This is what nitrogen is. Does that make sense? That's what you should draw first. Now draw me the hydrogens. Because ions are covalent. So this thing is, because this is outside of 17, this acts like a non. So your xenon does. So you share exactly how you draw it is what it's looking like. And so now you redraw this one in the middle. And you put these ones where you should. So they'll overlap. That and I'll redraw the original bottom up. That's always the last step. Okay. You guys redraw with the overlap on that. You guys redrew with the overlap on that. Yes. What you had was perfect. Yeah, so it's the seven. You haven't done everything on your way out. What you have to do. So in this one, that's your hydrogen. 1, 2 more. And then you'll see that they're gonna, because nitrogen is outside row 17 or column 17, it's gonna hydrogen behaves like a non-metal. So a non-metal share like this. Okay, if you're ready to move on, finish up what you've got. But some of you are ready for one more. So don't erase what you, if you're not done, don't erase what you have. Finish that one up. But I'm going to give one more for those who are ready for it. I was able to check in with all of you. That's great. I want you to do, I gave you Na2S. So I want, let's go. Yeah, let's do it. We're going to do this. I want you to do here, write this down. BE3. Write this down. BE3. N2. That's what I want you to draw. You got lots of space on the whiteboard. I don't feel super bad about this. BE3 N2. You don't feel bad about this? Because of all the space. If I need to do this on a piece of paper, I'd feel bad. Would you all the whole whiteboard you do? You're good. BE3 N2. And nitrogen. last one. When you're writing the notes, these numbers are these numbers always go down. First, identify what it is. Is it ionic? Is it covalent? What's wrong with it? It was cool. There's lots to draw. There's no reason one person should do all the drawing right now. You're drawing at 3 Ds, you're drawing at 2 ends. If you need another pen, go get another pen. Get everyone in on this. So is this thing ionic or covalent? Covalent means two nonmetals. Is that what you have? Where's your periodic table? Oh, let's take it. Remember, on the periodic table, this line separates the metals over here and the non-metals over here. So BE is over here, which makes that metal. And over here, non-metal. So the metal and non-metal. So it's not covalent. It's ionic. So they should be sharing. Remember, if the outside shell is empty, you don't need to include it in your next step drawing. One circle. This guy. Yeah. doing? You done? I actually want to see the last step drawn out. I'll just put it 3-2. No, I won't draw. They haven't earned that right yet. No, good. So that's the last step. With all the miles. Okay. Why? Right. So every electron that this thing gains is more and more negative. So the drawing looks good, you just gotta fix that charge. That's it.
I like what you have.
I like what you have.
What did you do? I was gonna add a body.
When
Let's get back to our station. We're going to do more I know. I have an idea. Okay, what we're going to do.
All three of you are happy with that? Okay, I've walked around, I've seen everyone. There's 15 minutes left in the block, and I am still going to do a lesson today. So I'm happy with what I've seen. I think some things have been clarified. Are we feeling a little bit better about these concepts? Even going back down talking about what's ionic, what's covalent, and then how these things behave. I want to take a quick picture of this board, just so I don't forget what I'm doing, guys. Okay, you guys can return to your dad. Please erase what's on the board so that my next class doesn't have all the answers to the questions I'm going to give them.
Can we get the drawings?
The drawings can stay. Well, like your extra bonus drawings can stay. I want all the board diagrams off the board. And then return to your desks and find me this page, Lewis diagrams. Yeah, real quick. Okay. Okay. Ooh. Massey, and I don't remember who you were working with. Yes, could you erase what's on that board there? Your picture, like the pictures can stay, but I want all the board diagrams gone. Cool, thank you. Okay, so I think we can appreciate that board diagrams are a lot of work. So they're not always the most useful tool because they are so much work. What was the only part of the board diagram that ever did anything when you guys were doing those drawings? The only part of the board diagram that ever actually mattered was what part? Yeah, but where did you connect them from? Like whenever you took electrons, where did you take them from? Wherever you put electrons, where did they go? It was always an outer shell to an outer shell. Whatever happened on the inner shells never actually mattered. It was that part was just a lot of extra work. And so that was noticed by a gentleman whose name is, there should be a G here, chemist named G.N. Lewis. Appreciated board diagrams for what they were, but recognized that, like you guys have just kind of mentioned, the outer shells are the only ones that actually did anything. So who cares what happens on the inside? If we can do the same thing we just did, but just on the outside, it would save us a lot of time, save us a lot of work, save us space on paper. So what this guy did was, G.N. Lewis, this I don't think you do in grade 9. Most of you wouldn't have done it in grade 9. G.N. Lewis developed a system of arranging dots, which sounds a lot like Bohr. He's developed a system of arranging dots around the symbol for an element. This is different already from the board diagram. In the board diagrams, I had you guys writing PN on the inside. Lewis said, nah, forget all that. We're just going to throw the elemental symbol down and to represent the atom and the valence shell. Now remember, the valence shell is only the outside shell. As that atom, or as it, gets ready to bond. So he developed a system for, I'm just going to throw down the symbol, and I'm going to throw down the dots. So here's how it would contrast. So if you're drawing a board diagram for fluorine, we'd draw it like this. We'd say, okay, well, there are 9 protons in fluorine. It has a mass of 19, so 19 minus 9 is 10. You get the neutrons. Fluorine is in row 2, so it would have 2 rings, and it would look like this. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. That's what the board diagram would look like. If you're reacting these things with each other, we don't actually care about anything that goes on inside this outer shell. So what Lewis did, he said, okay, well, forget all that. Let's just write down the F. Because I can always go look at the table. If I needed the protons, I needed the neutrons, I can just go look at the table. Just write down the symbol. And then he said, okay, all we actually care about is that outside shell. So how many electrons are in that outside shell? Well, there's a shortcut for that. That's not even a shortcut. It's a technique for using the table. When you're using the table, the group that the thing is in tells you how many valence electrons it has. And the valence electrons are the outside electrons. So group 1, so that first column, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, all has 1 valence electron. Group 2, beryllium, magnesium, calcium, strontium, barium, and radium have 2. We're skipping that whole middle chunk, and we're going all the way over to group 13. 13, 14, 15, 16, 17, 18, you only look at the ones column. So guys like boron and aluminum in group 13 would only have 3 valence electrons. Group 14 would have 4, 15 would have 5, 16 would have 6, 17 would have 7, and 18 would have 8. So then fluorine is in group 17. Okay, well, if it's in group 17, that means it has 1, 2, 3, 4, 5, 6, 7 on the outside. And that's all we care about drawing. And we draw it similar to how we would do a Bohr diagram. You put 1 in each spot and then start doubling up. But Lewis said, oh, that's all we care about, just the outside. So it makes our life a lot easier. So much quicker to draw. We don't have to do any math to figure out what the protons and neutrons are. We don't have to draw all the rings. All we care about is how many are on the outside shell. And then that's the only one we draw. So much easier. So then if I wanted to ionize fluorine, there's their fluorine atom. If I wanted to draw a fluorine ion, well, the charge, we can even look here. What's fluorine going to do when it becomes an ion? Is it going to give up all these 7, or is it just going to take one more? It's going to take one. So then the atom would just look like this. Boom, 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 boom. It's full now. So you draw the brackets and the charge. The brackets and the charge are the same. How you place the dots around is the same. We're just doing a lot less work. It's going to make everything a lot quicker. So, some people like formal rules. Here are the formal rules. When you're drawing Lewis diagrams, you write the symbol for the atom or the symbol and the charge for the ion. Determine the number of valence electrons it has. Remember, the valence electrons for the atom comes from the group or column number the atom is in. Groups are columns on the table. And then depending on whether an ion is positive or negative, it'll be empty if the thing is positive. So if you're drawing a Lewis diagram for a lithium ion, for example, there will be no valence electrons because lithium gives everything away. Or it will be full if the thing is negative, depending on whether they are metals or nonmetals. So, for example, let's flip the page. You've got a chlorine atom. What's the symbol for chlorine? Cl. Cool. What family or group number is chlorine in? 17. So how many valence electrons is it going to have? 7. 1, 2, 3, 4, 5, 6, 7. We're done. No rings, no layers. That's it. Bromine as an ion now. Bromine is what symbol? It's Br. It's also in what group? It's also in group 17, but it's an ion, so we don't actually care. What's the charge on bromine? When it ionizes, it's going to be -1. Well, actually, we do care what group it's in. It was in 17, so it would have 7, but -1 makes it, if it's -1, it gains. So it went from 7 in the outside shell to 8. 1, 2, 3, 4, 5, 6, 7, 8. Put the brackets and you're done. Let's go over to beryllium. What's the symbol for beryllium? It's Be. Some of you guys know your tables really well. Beryllium's in what group? It's in group 2. So how many valence electrons does it have? Just the not the ion charge, just the valence electrons. It's in group 2, so it's got 2. It's got 4 electrons total, but we only care what's going on the outside. 2 in the outer shell. 1, 2. Beryllium atom is done. And then the last one. Calcium ion. Calcium is what symbol? Ca. It's an ion. So is calcium a metal or a nonmetal? It's a metal. So when a metal ionizes, it loses everything in the outside shell. So that's all you got to do. What's the charge on calcium? +2. There are no dots to draw because when a metal ionizes, it loses everything. So there's no dots. You're done. And that's it. That's all we're going to add today. Tomorrow is a short block, so we're looking at making compounds tomorrow. I want you to do these 9 questions down here at the bottom. You can get, honestly, you can get these 9 questions done in the next 4 minutes. Draw me Lewis diagrams for these questions. On your mark and say giver. You can absolutely get that done in the time you have. Yes.
When the bell rings. Okay, my friend, when the bell rings, we'll meet. Yeah. We're going to choir.
Sometimes they leave early.
That was great. I never tried to do that. Hello.
Steve, stay in here, buddy.
That's awesome. Well, yeah, I just tried to keep this. That's fun. So, for choir,
Hey. Yeah. I want just the back page. You keep this and you buy that. Then on the side says D.
Yeah.